All right, I think we're rolling. Okay, good, good, good. Welcome. This is going to be a tutorial on force balancing, and the topic is part of a series of topics that are included in Physics 1, which is what I'm going to be educating on in this example. And we're going to explore force balancing with some obscure object. Now, this object, I'm going to give the dimensions of a box, but this object could be anything. It could be a brick, it could be a box, it could be a car battery. But we are going to talk about forces that this object will experience. And if this object has mass, and we're going to assume this object has mass, then it is guaranteed to experience all the forces the universe has to offer. But we're only going to consider a few for this example. Now, one of the most common forces that you experience is the force of gravity. And if you are on Earth, that's what keeps you glued to the planet. Now, you might be asking yourself, if there's a force acting on you, then how come you're not moving? Well, that's because all the forces that are acting on you actually balance out to equal a net force of 0. So if you aren't moving, if you aren't accelerating, then there is a net force of 0 acting on you. But you have the force of gravity pulling you downwards if we assume the planet is downwards from you, which is a relative term. And we don't know what force balances that out. So what force is that usually balances you out? That force is called the normal force. And that normal force occurs when two objects with mass collide and push up against each other because they're solid, and there are electromagnetic forces that prevent solid objects from intersecting. So this is a primitive example, but we are going to look at a different kind of normal force. And this force we're going to be exploring is called the buoyant force. The buoyant force occurs if you stick an object or drop an object in a fluid or liquid. Now, the buoyant force is very interesting because the force isn't necessarily acting on the object itself. It's acting on the fluid that is displaced, which in turn is affecting the object. So, I guess you technically can say it, but it is due to the liquid being displaced. So if you stick your hand in a jar of marbles, you displace those objects. And if you apply the same principle to grains of sand, the same would apply. What a liquid is just a concentration of very fine particles that move fluidly. So the principle is the same in that regard. Now, for this example, we're going to assume that we're going to drop this brick or this car battery into the ocean. And because we're assuming this, we can assume standard room temperature, let's say, and standard air pressure, because if you're at the surface level of the ocean, you're experiencing 1 atmosphere of pressure. And because of this, we can assume that the density, we're going to designate with rho, rho water is equal to 1 gram per centimeter cubed. Right. So the density of the water under these conditions would be 1 gram per centimeter cubed. Now we have this object right here, and we would like to know if this object would float or sink. So we need to know a little bit more about this object if we want to determine that. So we need the dimensions of this object. Let's say width. We need the length. And we need the height of this object. So if you remember, volume equals width times length times height, right? And we are going to give these dimensions. So we'll do width equals 3 centimeters. Say length equals, sorry, that L is a cursive L, so it might look a little bit wonky. 8 centimeters. And we're going to give it a height of, let's say, 5 centimeters. So we have our volume right here. We would also like to know the mass. But instead of getting the mass straight away, I'm going to give you this formula right here. It says mass equals density. And in this case, this density is volumetric density. Density times volume. So that's the formula we have for mass. And we have the density of water right here. Now we need the density of this object. So let's say the density of this object, density of this object, let's give that a mass of 5 grams per centimeter cubed. The reason why I picked centimeters for the dimensions is just so it could easily cancel out with this. Now we can, of course, do transformations between different magnitudes of the dimensions, but for this example, it's not particularly necessary, and I'm going to assume that you already know how to do that. It's fairly simple. But anyways, so we have the density of the water, we have the density of the object. We want to know if this object will sink, if this car battery will sink, and we're assuming that it has the dimensions of a brick likewise. So how do we know that? Well, this object will sink if the buoyant force acting on this object is less than the force of gravity acting on this object. Now remember how I said if the net force acting on this object is 0, then this object isn't moving. Well, if this object is sinking, then the net force isn't 0. And if it's sinking in particular, that must mean the force of gravity, which is acting downwards, is greater than the force of buoyancy, which is acting upwards. So the force of gravity would need to be greater than the force of buoyancy if this object is sinking, right? So how do we get the forces right here? Well, if you remember, force equals mass times acceleration. I know it's a weird A. This is the general formula for force. And we know that the acceleration due to gravity is 9.8 meters per second squared on Earth. Now, we're assuming it's constant, but technically it isn't constant. It depends on height, but the differences in height are so minuscule that it doesn't really matter, so we're just going to pretend it's constant. So we have the acceleration due to gravity here. We have the formula for force. Now we need to know if the buoyant force acting on this object is less than the force of gravity acting on this object. So if I were to take my hand and I were to force the object into the water and submerge it completely, then would the force acting on the displaced water due to gravity be less than the force of gravity acting on the brick? So let's determine that right here. So we have our formula. Where's the cursor? I lost the. Oh, there it is. Okay. So we have the formula for mass. So F of B. Remember the force formula right here. F of B equals mass of water. The mass of water being displaced times acceleration. Is that less than the mass of the object times the acceleration due to gravity? You know that A is on both sides of this equation, so we could just eliminate A like this. So is the mass of the water being displaced less than the mass of the object? So let's determine that. We have the density right here, density of water, if you remember this formula right here. So you have the density of the water times the volume of the water being displaced. The volume is width times length times height. So that's this identity right here is V. Is that less than the density of the object times the volume of the object? The volume of the object is V once again, and if you notice, V is on both sides of the equation once again, so we can cancel that out. So is the density of water less than the density of the object? Now, if we look at these densities right here, we can see the density of water is 1 gram per centimeter cubed. The density of the object is 5 grams per centimeter cubed. So this is true. This is, we're going to put a yes. So that means the buoyant force is less than the gravitational force. So because the buoyant force is less than the gravitational force, this object will sink. But let's say we give a value to the density of the object that makes it so that it won't sink, so that it'll float or it'll be buoyant. Let's give it a density that has to be less than or equal to 1. Let's give it a density of 0.21. Now, we know that it'll float because the density of the object is now less than the density of the water, but we don't know to what extent it will float. Part of the object might be submerged into the ocean, let's say. Part of the car battery could be submerged. So we need to figure that out. We need to figure out how deep would this object be submerged. So let's do that. Let's erase all of this right here. So in order to determine that, we need to determine at what points, 1 second, pick red. So at what point does the buoyant force equal the force due to gravity? Right here. And in order to know that, we would need to know some value of h, some cutoff value of h that would be submerged. So that's what we're looking for. If we type out these identities, right? So we're assuming that the base of the object, the width times the length, is parallel to the water that's going to be sinking. So neither the width or the length are going to change. They're going to be constant. So if we do mass water times A equals mass object times A. You can cross out A once again. So at what point does the mass of the water equal the mass of the object? Well, in order to do that, let's figure out the mass of the object, because we could probably simplify this even further. Now we know the density of this object is 0.21, and we have the volume right here as width times length times height. So if we put all this into a calculator, we multiply this together. We remember mass equals density times volume. Volume equals width times length times height. Then mass equals the density times the width times the length times the height. So we put that into a calculator, and we do 3 times, oops. That's not letting me. Row. Okay, there we go. 0.21 times 3 times 8 times 5, I believe. And we get 25.2. So 25.2 is the mass of the entire brick. So you do MO equals 25.2 grams, right? So at what point does the mass of water equal 25.2, right? We have the formula right here. So mass of water equals density water times volume equals 25.2 grams, right? That's what the mass of the object is. And we have volume equals width times length times height, but we don't know what the height is, because the height of the volume of the displaced water is going to be different from the volume of the object. So even though the width and the length are the same, the height will be different. So we have density of water times width times length, so that's 24 centimeters squared. It's the area of the base of the object. And if you remember, volume is the base with big B times the height. And base with the big B is just width times length here. And we have the height. And we have 25.2 grams on this side. So density of water is 1 gram per centimeter cubed. So 1 gram per centimeter cubed times 24 centimeters squared is 24 grams per centimeter, right? Because we canceled out centimeter squared, but we have centimeter cubed, so we still have 1 centimeter at the bottom, times height equals 25.2 grams. And you'll notice grams is on both sides, so we can cancel that out. And we can multiply both sides by centimeter. So we get 24 H equals 25.2 centimeters. And we can divide both sides by 24 to get the final answer for the height. And we'll get height height equals, let's put this into a calculator. So 25.2 divided by 24, 1.05. So 1.05, let's go back here. 1.05, and that is in units of centimeters. So if we drop this car battery into the ocean, it would be a very light car battery, but it would be submerged 1.05 centimeters into the water. So this, one second. So this amount of height would be submerged into the water, and the rest of the value of the height would be above water. So if we subtract this from 5 centimeters, we get 3.95 centimeters. So 3.95 centimeters of the object would be visible above water. And this is how you can apply force balancing, particularly to buoyancy. I hope you found this video instructive, and I hope you found it helpful. And I hope you have a wonderful rest of your day. Thank you for watching. And I will now end the video here.